19 neurons and a forest. A drone navigated a dense forest at 40 miles per hour, using a neural network consisting of only 19 neurons. While most developers were busy trying to squeeze billion-parameter transformers onto edge hardware, the team at MIT demonstrated that structural complexity beats raw scale for temporal data. This architecture, known as a liquid neural network, replaces the fixed weights of traditional models with continuous time differential equations. It is the first instance we have seen of high-speed physical navigation handled by a system smaller than a single pixel of an average LLM. This efficiency stems from a fundamental rethink of the time dimension: continuous time versus static snapshots. Traditional architectures treat time as a sequence of static snapshots, much like frames in a film. Liquid networks instead use ordinary differential equations to define the state of a neuron as a continuous flow. In the 2025 benchmark tests, these models maintained stability even when the input data frequency shifted unexpectedly. By making the synapses function as dynamical systems, the model adapts its behavior in real time based on the input signal it receives. This adaptation leads to a massive reduction in the actual compute required for inference. The Scaling Law Counterpoint. Scaling laws suggested that performance requires more parameters, but the liquid approach suggests we have been using the wrong math for physical tasks. For a standard lane-keeping task, a transformer-based model often requires 300 million parameters to achieve 98% accuracy. A liquid model achieves the same results with just 80,000 parameters by solving for the underlying physics of the movement rather than just memorizing patterns. However, there is a catch that the marketing blogs often ignore. The mathematical complexity of solving these differential equations makes them significantly harder to parallelize on current GPU architectures compared to simple matrix multiplication. Even with these parallelization hurdles, the real win is how these networks handle noise. The robustness factor. Out-of-distribution data is the graveyard of most autonomous systems. When a standard vision model trained on sunny roads encounters a heavy snowstorm, its confidence scores collapse because the pixel distributions no longer match its training set. Liquid networks are more robust because their fluid parameters allow them to adjust their internal time constants on the fly. Data from the recent 2026 Robotics Summit shows that liquid architectures maintained operational safety in 84% of edge cases where transformer-based models suffered catastrophic failure. They do not just recognize patterns, they model the causal dynamics of their environment. This fundamental shift in architecture points toward a specific future for autonomous hardware: the signal under the noise. The move toward liquid architectures signifies the end of the brute force era, where every problem was solved by adding more layers and more data. Liquid networks prove that architectural efficiency and continuous time modeling are the only viable paths for local, low-power intelligence in robotics and sensor fusion. Based on the parameter efficiency and noise robustness shown in the MIT and autonomous driving papers, the industry is moving toward a hybrid model. In this setup, transformers handle the high-level reasoning, while liquid networks manage the real-time physical interaction. This solves the latency and reliability issues that have plagued edge AI for the last 5 years. For builders and engineers, the takeaway is clear: stop trying to shrink massive models and start implementing architectures that natively understand time. Watch for the upcoming release of the Liquid Integrated Robotics Stack from the major warehouse automation players in Q4 of 2026. Subscribe for more,